start, take a look at this satellite imagery. It's from a project at King's College London, unrelated to my work, but it uses the reflectance of leaves to identify areas of forest being felled in close to real time, and it's called Terra I. I put it up because it uses a characteristic of the intact forest, the greenness of the leaves, and it monitors it using satellites, a form of vegetation monitoring. My work focuses on the continent of Africa, and I'm interested in the extent to which remote sensing could be used for biodiversity monitoring, and whether traits, such as plant height, can be monitored using remote sensing. So in 2012, parties to the Convention of Biological Diversity started a process to develop essential biodiversity variables, standardised measurements for long-term monitoring of biodiversity, and the usefulness of monitoring plant traits will be increased if we better understand the relationship between those trait values and the species richness in different biomes. And that's what my work looks at. And additional reasons why understanding the spatial distribution of plant traits is useful include the growing appreciation of the public benefits of certain plant traits, so soil organic carbon being closely related to the leaf traits in the area, and also earth system models where plant traits both affect and are affected by changes in climate. So over the next 9 minutes, I'm going to try and tell you about two different sources for plant traits. I'll show how trait data can be used to compare functional diversity of plants in different regions of Africa. And I'll show how species distribution modelling can allow comparisons of functional diversity at a finer scale. And I'll give a glimpse of how traits of plants from model species distributions can match up to remote sensing products. So I work with a random sample of species, 586 species of flowering plants from across the continent of Africa. And the pie chart shows the proportions of different growth forms in that sample. 586 species only represents 1% of the 60,000 species known from the continent. I collected data on both plant traits and the spatial distribution of these species. So which plant traits should I consider? This is a diagram from work by Professor Sandra Diaz. She highlighted a resource allocation trade-off between species with long-lasting leaves and species with short-lived leaves. And a trade-off in these diagrams is indicated when the arrows point in opposite directions, so where there's a negative correlation. Mark Westerby has argued that leaf traits, seed traits, and plant height are sufficient to identify the broad ecological strategy of plant species. And trade-offs are best shown by these sorts of continuous traits. So I compared trait data from two different sources. The TRI database, which is online and is largely based on in situ measurements. And I also found a taxonomic description for each of those 500 species. And I benefited from the recent completion of, or near completion of, several African floras. Only 4 of my chosen species had values for all 4 traits in TRI. And so the traits that I obtained from species descriptions were plant height, seed volume, leaf area, and the number of seed per fruit. And I obtained comparable traits from TRI Online and extracted 4 traits for all the species in the database that are known from Africa. So this sample of species from the TRI database on the right is definitely not a random sample. It contains different species from the sample that I took from taxonomic literature. And as hoped, on the left, the geographic distribution of random samples is broadly representative of species richness, so I've got between 0.7 and 1% of known species from those regions. Whereas from the TRI database, you get a much broader range from 0.2% to 6.5%. And the dominance of the European species within that database means you get far more information about the traits in Northern Africa. So both data sets support what Sandra Diaz showed to the extent that not all combinations of traits are possible, and the white space in these diagrams is evidence of that. But both charts also show a widely recognized trade-off between the seed number and the number of seed per fruit. Ecological filtering, as described by Professor Paul Keddy, offers a framework for thinking about the geographic distribution of plant traits. So over time, both abiotic and biotic filters in a location retain particular combinations of plant traits suitable to the local situation. And in areas where abiotic convergent filters are strong, you would expect the range of traits to be narrow and constrained. So one way to consider spatial variation in trait values is functional diversity, and I use two metrics of functional diversity: functional richness and functional dispersion. And these diagrams show two traits, but these measures can be expanded to many traits. I'm considering plant height, seed size, leaf area, and the number of seed per fruit. And when considered together, this can be considered a form to form trait space. Each species, represented as a blue dot in these diagrams, will have a different position in trait space. A geographic locality where all the species are morphologically similar will have species points in trait space that are tightly clustered together, or if the points are more widely distributed, then that's indicating higher functional diversity. Functional richness is a multidimensional range, so it's the area or the volume enclosed in trait space for the species in a particular location. Whereas functional dispersion is a multidimensional average. It relies on locating the centroid in trait space for those species from a particular region, and then looking at the average distance. So this is functional diversity across different regions of Africa, with each line being a different region. The black dots show biodiversity metrics for each region and dataset, and the blue lines are null distributions. So if you imagine a table of traits for each species, the null models are created by randomly shuffling the species names against those trait values. And if a black dot is to the left of those blue lines, then this suggests that ecological filtering is occurring. The top two graphs show functional richness, with the random sample on the left and the trice species on the right. And in that random sample, Southern Africa has the highest species richness and also the highest functional richness. But none of those show any evidence of filtering. In the bottom two graphs, the random sample of traits in Northern Africa and Southern Africa are tightly clustered around the centroid, and at a regional level, functional dispersion suggests that that's where filtering is taking place. I used regional analyses at that stage because I didn't have detailed locality information for all the species in the TRI database. But in contrast, I compiled locality information for the randomly sampled species. And these maps are based on stacked Maxent models, producing species richness on the left. The functional richness map in the middle is based on the convex hull of trait space calculated for each pixel, whereas functional dispersion is the average distance to the centroid. As with the regional analysis, this suggests that functional richness is more strongly influenced by species richness than functional dispersion is. So just as with the regional analysis, you can create a null model, you can do that at a finer scale. And so these maps show the areas where you have far less functional diversity than you expect. And you get this difference between functional richness and functional dispersion because of the slight difference in the way the metrics are calculated. And then going on to compare this to remote sensing products, This map shows the similarity between plant height classes predicted by my species distribution models and the plant height classes from satellite-based LiDAR. So I used a product, a LiDAR product, that it shows plant height classes produced by Dr. C.S. Loss. So on these charts, each bar is a different height class for a particular pixel. So these are from 3 pixels that show good agreement between my model species and what's detected by satellites. And the limitations in both the LiDAR product and the representative of my model species probably results in the areas where they don't agree, shown here in reddy brown. But I'll be exploring more about the extent to which such remote sensing products could be used to infer functional diversity. So, in conclusion, I genuinely think that the traits in species descriptions can form a basis for understanding functional diversity. I also think that taking account of species richness when using this sort of trait data is really important. And understanding the geographic areas where there is high species richness but also high redundancy in the plant trait values of those species is important if plant traits are going to be used for biodiversity monitoring. And it will be important to establish standards as to what functional diversity metrics should be calculated for this sort of work. I'm grateful to my supervisors, Neil Bremmett and Mark Mulligan, and thanks for listening. I'd be grateful for any questions.